Možete vi slobodno pljeskati. Even being near your computer with Max Planck on it makes me shiver. So thank you so very much for being here with us today. You can leave your award here. Let me just give a short introduction to your lecture. Dakle, rođena u zoru novoga tisućljeća, atomsna fotografija otvorila je vrata za snimanje subatomskih gibanja dok se razvijaju u vremenu. Više o ovoj temi naravno reći će nam profesor Krausz, koji je za svoj doprinos u uspostavljanju polja atosekundne znanosti nagrađen među ostalima i Nobelovom nagradom za fiziku 2023. godine. Dakle, dame i gospodo, velika nam je čast imati ovoga čovjeka ovdje na ovoj pozornici. Na redu je plenarno predavanje profesora Ferenca Krausa na temu subatomska gibanja, od praćenja elektrona do ubrzanja obrade signala.
Thank you. Good morning, ladies and gentlemen. It is a tremendous pleasure for me to be here today and receive this prestigious Tesla Egg Award. I thank Krausz and the prize committee for bestowing this honor on me. It is truly special for me to be here, given that this conference is organized by a learned society which represents the field where I come from. I majored in electrical engineering a long time ago, but very quickly converted to a physicist. And that's how actually this very conference happens to be the first one organized by electrical engineers, which I attend during my scientific career as a researcher, which started some 30 odd years ago. So it is a true pleasure, and it is also what makes it also very special. This is not just one conference organized by electrical engineers, but I think it is one of the most innovative ones. You were among the very first going online, actually before COVID. Very few conferences in the world did that. Most of them just learned how to organize a hybrid conference, basically enforced by the situation that was caused by the pandemic. But you led the world in that respect. We did this before the pandemic came about. And not only that, you are one of the very few who also organize a translation into 60 languages. And I was most impressed to learn that you just started a couple of years ago using large language models for evaluating and even ranking the submitted conference contributions. Briefly, you are defining the frontiers in disseminating information and promoting scientific research in the 21st century. Congratulations, wholehearted congratulations to the organizers. Me here. So with my lecture, I would like to deliver an example of the eternal, what I believe is an eternal truth of Max Planck. The more delicate the details are by which we can follow nature on any path, the richer and more lasting will the gains be that we can draw from this perception. In my example, the delicate details will be electronic motions in tiniest dimensions, both in space as well as in time. And one of the hopefully lasting gains will be the advancement of electronic signal processing to its ultimate speed limits. And of course, we also want to figure out what that ultimate speed limit is. And I think this first part of the challenge is almost done, as I will report to you in the following few minutes. I will address more specifically how subatomic motions of electrons can be initiated, controlled and captured by light, and how the ability to control their sub-nanoscale motion with the electric field of light paves the way for pushing the frontiers of electronics to its ultimate speed limit, to the frequency of visible light. As you will see, we are using controlled electric fields to control electric current in small dimensions in the very same way as micro and nanoelectronics has been doing it, with the only difference that in our case, in the area which we have dubbed light wave electronics, the electric fields oscillate 10 to 100,000 times faster than they do in cutting-edge microwave electronics. We all know how transistors allow the control of electronic current in nanoscale circuits with microwave electric fields that oscillate on a picosecond time scale. And how this control enables sampling of electronic signals in macroscopic circuitry with picosecond time resolution. What follows, I'm going to show you that control of electron current is also feasible with the electric field of light. This control utilizes 1,000 times stronger and about 1,000 times faster oscillating fields, permitting the exploitation of nonlinear effects and thereby opening the door for observing electron phenomena in atomic dimensions with several 100,000 times higher attosecond time resolution. The story I'm telling you started about 100, actually pretty exactly 100 years ago. We are celebrating this year the year of basically the anniversary, the 100th anniversary of the birth of quantum physics, quantum science, which started back in 1925 when in Vienna Erwin Schrödinger created the equation predicting and describing the quantum mechanical motion of electrons in atomic dimensions. Some 3/4 of a century later, at the dawn of the new millennium, Schrödinger's prediction of subatomic motion could be verified experimentally by capturing subatomic electron phenomena in real time, again in the same city, in Vienna. Two major discoveries at the middle of this 75-year time span between 1925 and 2001. Two major discoveries around the middle have been decisive for the emergence of this technical capability. The laser, demonstrated by Neyman back in 1960, utilizing the concept of a stimulated emission discovered by Towns, Prokhorov, and Basov, and the theoretical prediction of Keldysh, also around the same time, a few years later, that ionization by electron tunneling may occur with substantial probability within the half-wave period of a sufficiently strong optical field. Based on these two major milestones occurring in 1960 and 1964, several advances paved the way to the birth of attosecond science, with the key of them being the generation of intense fuse cycle, actually close to single cycle, near-infrared laser light, which carries which carry a substantial fraction, more than 50% of their overall energy within one single oscillation period, basically the center cycle of this wavelength. The first powerful near single cycle light pulses of this kind have been generated in Vienna in the mid-90s in the framework of a multilateral scientific collaboration. I will briefly refer to these pulses just as single cycle laser pulses or waveforms. If atoms in the gas phase are exposed to such a single cycle laser field, their most weakly bound electron can be liberated by optical field induced tunneling predicted by Keldysh half a century before. Within a fraction of the oscillation period of light, and this very process, this liberation of the electron within the central half cycle of this laser field has been the key for the generation of the first attosecond duration pulses of light, in particular ultraviolet light, in our laboratory at the Vienna University of Technology by Michael Henschel and Reinhard Kimberger back in 2001. The vacuum chamber in which these first isolated attosecond events in the form of an XUV burst were measured is meanwhile, since the 1st of December 2024, on display in the permanent exhibition of the Nobel Prize Museum in Stockholm, as a consequence of this most memorable event of my life, which had happened a year before. In order to be able to tackle real-world challenges, such as exploring and pushing the frontiers of contemporary electronics, attosecond technology, so far relying on complex vacuum systems, as you see on this picture, it's quite a complicated system, to requiring several scientists around to keep it happy and do it what we want it to do. Obviously, this first generation of attosecond technology had to become simpler and more powerful to make it really useful for some real-world applications. And this milestone was recently enabled by the single-cycle light pulses that I introduced you before, owing to its ability to realize the same process in wide bandgap solids that attosecond ultraviolet light generation is based upon in atoms. Optical field induced electron tunneling from the valence band, where all the electrons reside in the ground state of such a solid, basically. That's the normal ground state in an insulator. There are no free carriers in the conduction band around, and that's why the thing isolates and doesn't conduct electric current. But if we apply a strong enough light field, then the strong light field bends the band structure, as you saw on this graph, and if it bends it strong enough, then the electrons can tunnel through this narrowed Coulomb barrier, this blue line, and by this tunneling they can be promoted to the conduction band, and all of a sudden we turn an insulator to a conductor. And as you will see, this opens the door to a new way of doing ultra-fast measurements, actually for the first time in a solid-state device on the attosecond time scale, which we actually dubbed attosecond technology 2.0. But why did I actually emphasize that we need for this a single cycle laser field? Why is the confinement of this process to a single field cycle indispensable here? Because no solid matter could otherwise survive the required critical field strength, which is in the case of, for instance, quartz, with a band gap delta G in this formula about 10 electron volt. No solid matter could survive the required electric field, which is in this particular case about 2 volt per angstrom. If we would use a longer laser pulse, this would, at this field strength, the laser pulse would cause basically an optical breakdown, and the solid material would be destroyed. And of course, this is not a mode of operation that we can afford. When we would like to do metrology, we would like to stay below this so-called breakdown threshold, and we stay below this only if this process is confined to just half a cycle. Then the material can survive even such a strong field. So with a single cycle laser field, we can reach this very critical field strength without destroying the material, and we can realize this tunneling. The consequence is far-reaching. Tunneling can now indeed be realized, and with a cosine-shaped waveform, the electric field squared, of which we have depicted here by the black line, with a cosine-shaped waveform, we can confine actually the carrier injection into the conduction band to a fraction of the central half cycle, which, if we use infrared laser field with a cycle period of a couple of femtoseconds, then the half period is 1 femtosecond. And the fraction of this 1 femtosecond is obviously an attosecond duration, sub-femtosecond duration carrier injection. And this very carrier injection, confined to this extremely short period, now can replace sub-femtosecond XU or attosecond XU, and always obviates the need for complex vacuum systems. We can realize this process in a tiny solid-state circuit. And for a class of applications, this is as useful as previous generation, or even more useful actually as previous generation attosecond technology. And this class of applications is particularly important for you, for the technology that you represent. It is highly relevant for advancing electronics, namely by being able to interrogate. Control and interrogate valence and conduction band carrier dynamics that underlies the switching of electric currents in modern semiconductor circuitry. In a primary step in the new technology, we utilize this nonlinear carrier injection, basically, which is induced by the tunneling predicted by Keldysh half a century ago. We utilize this nonlinear carrier injection for probing optical fields in an approach that we've dubbed nonlinear photoconductive sampling. The tunneling process here is induced by the blue electric field, and the carrier injection is confined to this period depicted by the green pulse. And this very injection actually probes the electric field that is depicted by the red line here. And by scanning the carrier injection across the laser pulse to be measured, to be sampled, to be characterized, we have been able to actually trace out how the electric field oscillates, in this particular case by using a quartz photoconductive sampler. The technique has recently proven its capacity to sample light fields up to the deep ultraviolet. Up to frequencies, as you see on the frequency scale, up to actually about 1.5 or even slightly beyond 1.5 petahertz. You may actually consider, in your language, you may consider this as a kind of a petahertz bandwidth oscilloscope or transient recorder, but a very special one, obviously, that offers some 10,000 times wider bandwidth than the fastest conventional oscilloscope or transient recorder on this planet. as you also see, we can resolve here half cycles in this deep UV electric field that lasts only 500 attoseconds, indicating that our light-driven or light-controlled transient recorder must have a resolution of about 200 attoseconds or better. Light field sampling now provides a new probe for attosecond phenomena. The electric field of light from the infrared to the ultraviolet, it directly probes the arguably most fundamental consequence of any light-matter interaction, the displacement of electronic charge density, briefly polarization. It is imprinted in the electric field transmitted through the sample that we transilluminate with such a light pulse. Referencing this transmitted field to the input field allows for a thin, sufficiently thin sample, unambiguous retrieval of the induced polarization. Along with this driving field, this polarization depicted in green determines the instantaneous energy flow from the light field into matter and vice versa. You see here the formula of this rate of energy exchange, which is a formula that is supposed to be very, very, very familiar to you. Maybe not exactly in this form, because in electrical engineering you don't really use the induced polarization as a primary candidate, but what of course you use much more widely is the current density. And this temporal derivative of the polarization is nothing else but the current density induced by the electric field in the medium. So basically you see this is just essentially electric field times current. This is kind of power, right? Energy by time. So this is, you must be very familiar with this. This describes the rate of instantaneous energy transfer from the light field or from any field. Of course, the formula also applies to your microwave fields in the same way, but we are dealing here with light fields. So basically this describes how the energy is transferred from the field to the material and then from the material possibly back to the field. So obviously this energy exchange that's actually micro and nano electronics is all about, right? Just not with light fields, but in that particular case in our circuits, in my laptop. This formula works all the time, however, not with light oscillating fields, but with microwave fields. But it's of course widely valid for both fields. Here you see how this rate of energy exchange, if we integrate it from minus infinity, basically from before the pulse arrives in the medium, how this rate of energy, or actually the transferred energy density, is evolving in time during the fuse cycle or near single cycle laser field, which is depicted by the dashed line in both panels. In an insulator, in this particular case quartz, where it takes 6 photons to actually promote an electron from the valence band to the conduction band. That's why we refer to this as a 6-photon band gap, because the band gap of this quartz material is about 6 times the photon energy of the infrared laser wave that we apply here. And to compare, we did the same experiment also in another material with a much smaller band gap, a very well-known material to you, silicon, the fundamental, most important material in microelectronics, nanoelectronics. Here, the band gap is much smaller. It takes only 2 photons to promote the electrons from the valence to the actual convection band and kind of create carriers. So what we see on the left-hand side, this for high field strength, and on the right-hand side of the panel we list the peak electric field. For the upmost curve, for the blue curve, it's 2.7 volt per angstrom, and then we gradually reduce it. As you see, for the highest field strength, the energy transfer is kind of irreversible. It stays up, the transferred energy, after the pulse is gone, after the few oscillations of the black line basically disappear towards a time somewhere around 20-30 femtoseconds behind the peak. The transferred energy stays constant. Why is that? Because obviously at these strong fields, as we discussed before, the laser field promotes electrons from the valence to the conduction band, which of course takes energy. And that's why we see on the blue line and on the other lines the red and the green lines that the energy goes up. It takes energy to promote these carriers from the valence to the conduction band, obviously. But these carriers stay there for quite a while, for a much longer time than the duration of the laser pulse. They decay back to the valence band only on a time scale of picoseconds, which is much longer time scale than the window that I'm showing you here. And they decay actually in a way that is very detrimental for electronics. They decay in a way by actually creating a lot of heat, because a substantial fraction of their energy they transfer to the lattice, and the lattice starts vibrating, and the vibrating lattice is heat. So we start heating up if we are operating in this regime. And now imagine we want to utilize this for fast signal processing. So we would like to utilize this energy transfer very frequently, all the time, at ideally up to terahertz sort of clock rates eventually. So we would very quickly produce so much heat due to these carriers that we have created, that which would just cook our integrated circuit. And actually this is what limits contemporary digital electronics to a clock rate in the range of 10 gigahertz, which where it has been stagnating for quite a while, actually for about 2 decades meanwhile. I'll come back to that in a couple of minutes. But here I would like to draw your attention on an important fact. As you see, as we start reducing the field strength, and we reach a regime, and this is the red, the yellow line at about 2.1 volt per angstrom, where this transferred energy is completely going back to the field, because the line goes back to zero by the time the laser pulse has passed the material. So obviously, in such an insulator with such a big band gap, we can realize a regime of the light-matter interaction where we transfer energy very quickly, as you see, during the laser pulse, but this energy is also going back very quickly, basically within femtoseconds, to the field. And by the time the laser pulse has transmitted the material, the energy is completely extracted. So basically there is no energy left behind that could heat the material. But this energy exchange, of course, could be potentially used for optoelectronic signal processing, right? So we have found here a regime where potentially we could switch on and off some signals by energy transfer between the light fields and the material without dissipating heat. And interestingly, in the 2-photon band gap, there is no such regime. The dissipative and reactive nonlinearities there have the same intensity scaling, and therefore always, no matter at what intensity level, inherently connected. These studies showcase how real-time access to the light electron energy transfer allows exploring optimum conditions for ultra-fast optoelectronic signal manipulation. A related attosecond time resolved study yielded experimental evidence, actually the first experimental evidence for the electric current responding linearly to the electric field up to frequencies exceeding 1 petahertz and up to field strength exceeding 1 volt per nanometer, which is more than enough to drive measurable currents in nanocircuits. This response time of linearly induced electric current was measured in a material with one of the highest band gaps in excess of 10 electron volts and is likely to constitute the ultimate band structure related, band structure limited speed limit of classical signal processing. So we believe that we have now firm evidence that something around 1 petahertz is probably the highest speed at which we can possibly switch electric current on and off in materials that are existing on this planet, at least that have been known to exist at this planet with the largest band gap. And now the challenge is how to actually exploit this speed. We and apparently the editorial board of Physics World magazine believe that this is an important finding, given that Moore's law is about to coming to an end in the advancement of processor performance. Ever since the beginning of the new millennium, this advancement was largely driven by miniaturization, by putting ever more transistors in ever smaller space, whilst the clock rate was stagnating at about 10 gigahertz and still stagnates. The question that we are intrigued by is whether attosecond physics can possibly contribute to exploiting the fourth dimension for further advancing electron-based information processing. Our recent findings indicate that in principle, electric currents can be manipulated in solids some 10 to 100 times, 1,000 times faster. The question that remains, and this is the overriding question, whether this very capability can be extended to integrated circuits, to small dimensions, to kind of real-world circuits. If so, this could be the driver for further advancements of processor performance over the coming decades. This is one of the questions we continue to pursue with our ATOL team based in Munich and based in Budapest, and I would like to thank all members of this wonderful team for their invaluable contributions, and thank you for your attention.